Okay, welcome to another video. Today we're getting into the heart of the simplex method. So, reviewing what we covered in the previous videos, we found that if we have a linear program in augmented form, we can find all the basic feasible solutions. And that's what we did in the last video. But although there are only finitely many of those basic feasible solutions, it wouldn't be a good strategy to just try to list them all. It works for small problems. It's essentially what we did when we did the graphical method, but it's not how we want to work in practice when we're solving a linear program. Instead, the whole idea behind the simplex method is instead of checking all basic feasible solutions, we start at a basic feasible solution and then we move to another basic feasible solution, sort of moving around the boundary of the feasible region from kind of corner to corner. And we always move in a direction that improves our objective value, or at least doesn't make it worse. There's some times where you sort of have to move sideways and you see no improvement for that move, but then you're able to see some more improvement in a later move. And we won't worry about that too much to begin with. But there's this idea that we're going to move from corner point to corner point, or basic feasible solution to basic feasible solution, in a way that moves us around the boundary of our feasible region until we find the best solution. Okay, so some questions that we need to answer if we're going to do that is, how do we know where to start? How do we know where to move next? And how do we know when we're done? We're going to focus on 2 and 3 in this video. We're just going to save 1 for later. We'll give a pretty simple answer for number 1 for this video, but we'll have to dive into that in more deeply when our simple solution doesn't work out. So let's look again at Geppetto's problem in augmented form, but let's also introduce a variable z that tracks our objective. Okay, so we said we want to maximize 3 times the number of soldiers plus 2 times the number of trains, and we're going to say that that value is z. So z is going to be our objective value, and our goal in this case is to maximize z. And we're going to do a little trick in that we want all our variables on the left side of the equation. And so we'll subtract 3xs and 2xt over the other side, so that we have this equation here. And we're going to treat this equation just like we treat our constraints. It's a little bit special as a constraint because it's really our objective. We're going to put it in the top row of our system, but essentially we're going to take that augmented system now and add this to it. So if I think of my variables now that I've introduced, z is in my new variable. I'll always put it at the left side, just kind of out of practice. My original variables of xs and xt, and then I've got 3 slack variables, sf, sc, and sd, and then right-hand side. Okay, so first I'll take this objective and I'll actually put that in the top row. So I've got a coefficient of 1 for z, -3 for xs, -2 for xt. None of my slack variables show up, and so they're all zeros. And then my right-hand side, because I moved everything to the left side, my right-hand side ends up being 0. Okay, and just to show that this top row is actually the objective, I sort of draw a line to separate it out from the rest. I also like to draw a vertical line to separate out my right-hand side. And maybe also out of habit, I like to draw another line to separate out z. Z is kind of a little bit of a different variable. It's tracking our objective. Now, underneath that, I put all my constraints. And so we had our constraints from last time. Let me sort of pull those up here. And notice my z doesn't show up in any of my constraints. And so actually, I'm going to get 0 in there for each of my, for the coefficient of z, because it's not in any of the constraints. But my first constraint was 2x1 or 2xs, 1xt, 1 for my first slack variable, 0 for my other slack variables equals 100. 0, 1, 0, and 80 for my second constraint, and 1, 0, 0, 0, 1, and 40 for my third constraint. And this constraint was the finishing constraint, the carpentry constraint, and the demand constraint. Okay, so I've got my objective row, I've got my 3 constraint rows, along with this new variable z that's going to track essentially my objective. So, and this is actually, we give this a name. This will be what we call the tableau. And we're using sort of the tableau method. It's just a fancy way of talking about this special augmented matrix here. It really is just a matrix, an augmented matrix, where we've now added an extra row for the objective. Okay, so similar to what we did in the last video, now we're going to choose a basis. Okay, and this is really the where do we start question of where should we start, because we know that each choice of a basis corresponds to a basic feasible solution or a corner point. So to begin with, and for all the examples or the first several examples that we see this week, our choice for a basis will be pretty easy, in that our initial basis we'll always choose z to be in our basis. Some books actually kind of implicitly choose z to be in the basis and don't explicitly say that it's in the basis, but I like thinking of z as always in our basis, and then we're going to choose each of the slack variables to be in our basis to begin with. So SF, SC, and SD. So these are going to be all of our basic variables, and all the other variables, so maybe I'll make a note of it, non-basic, then would be my 2 original variables, XS and XT. So the non-basic variables, we're going to set each of these to 0. And then we're going to essentially read off the values of these ones here. Now, kind of the first step would be forming the B matrix here and sort of solving to get that into the identity. It turns out we've already got an identity matrix, or there are standard basis vectors underneath SF, SC, and SD. Okay, so if we set these two to be equal to 0, it's essentially the same as crossing off these 2 columns and ignoring them, because the value of those variables is 0. And then this first row, well, actually our objective row, if we set XS to 0 and XT to 0, then we get we get Z equals, that's 0, that's 0. These are all zeros for their coefficient. And then our right-hand side says equals 0. And so our initial solution has Z equals 0. That we can know from this first line. And actually, I'll kind of denote this row as the Z row. It's our objective row, and so I'll write that there. This next row, if I set XS and XT to be 0, and so essentially hide those, I can read off that SF is the only other thing that has a coefficient in that row, and it has a coefficient 1, so 1 times SF equals 100. And so we'll actually call this the SF row, and that one tells us that SF equals 100. SC, similarly, we can read off from this row. These get zeroed out, and we get SC equals 80 and SD equals 40. Okay, and this is actually one of our basic feasible solutions from last time. And then we can tack on that XS equals 0 and XT equals 0, because they are the non-basic variables. So that is our initial solution. Next question is it an optimal solution? We know, because we've solved this problem graphically, that it's not. This corresponds to the origin in the original units or in the original variables. It's not optimal, but how do we know that? Well, let's look at our objective. So is it optimal? And then we can say no, but why is that? Well, z, if we read off this first row, z minus 3xs minus 2xt equals 0, or actually moving these back over to the other side, z equals 3xs plus 2xt. Now, xs and xt are currently non-basic variables, meaning that they're currently set to 0. But the question is, if we brought one of those variables into the basis and made them not 0, would we improve our objective? And in this case, both of them, once we move them over to the right side, have positive coefficients. They're negative coefficients when they're on the left side, but they're positive coefficients once we move them over to the right side. And so increasing either xs or xt from 0 would increase z as well. Okay, this is the key idea of xs and xt are currently 0, but if we increase them from 0, brought them into the basis, made them non-zero, would that improve? And the answer is yes. So I'll maybe write that out. We can increase z by increasing xs or xt. Okay, so that's going to be the next step. We're going to change our basis. We're going to choose one, either xs or xt of our variables to come into our basis. We'll choose another variable, then we'll have to leave the basis because if we remember, when choosing our basis, we want essentially the basis to match the number of constraints. Now we sort of added an extra row, added z in there, so we're gonna always look for having 4 variables in our basis. And you can actually think of each of these 4 variables as corresponding to one of the rows. Okay, so there's one variable per row, and you'll notice that if I look at the columns for these variables, the standard basis vectors show up in the columns for z, sf, sc, and sd. And that's going to be the characteristic feature of our basis, is that the standard basis vectors are going to show up underneath our basis variables. Okay, and so when we bring a new variable into the basis, we're going to do elementary row operations in order to change whatever the current column is into the standard basis vector. Okay, so let's choose xs or xt to enter our basis. Now, either of them should improve our objective. There's a couple of rules of thumb that your book talks about of how to choose. They're mostly just heuristics. And as long as you choose one variable that improves it, and as long as you're kind of careful not to get stuck in a loop where you're sort of switching back and forth between variables, it really doesn't matter which variable you choose, as long as you choose one that improves your objective. So I tend to follow the simple heuristic of choosing whichever has the larger coefficient, meaning that the smallest change in either xs or xt results into a larger change in z. No guarantee that that's going to get you there in the fewest number of steps. Actually, in this case, we'll find that it will take us more steps using this heuristic, which is fine. More example, more video to show you. So looking at this, the 3 coefficient is bigger than the 2 coefficient. So we're going to choose xs to enter our basis. Okay, you're going to want a couple of extra sheets of paper for this. And so here I'm going to jump onto a new sheet of paper. So we're going to choose xs to enter the basis. Okay, which means that our new basis is going to have xs in it, but we've got to get rid of something else. And so let's look at our constraints that are up here and think about, okay, if xs, which is currently 0, starts increasing from 0, when does one of the other variables, sf, sc, and sd, are going to have to kind of compensate for that in order to maintain the inequalities here. Remember, we don't have inequalities anymore. We got equalities. So if XS increases, SF, SC, and SD are going to have to compensate. And the question is, as they're compensating, which one of those gets driven to 0 first? Okay, so let's actually write out what each of these constraints are, maybe not in augmented form, but actually as formulas, and let's look at those. So our first constraint up here is essentially saying 2xs plus 1xt plus sf equals 100. Okay, sorry, let me bring that up and I'll kind of just hide some of the work we had below. And our next constraint is xs plus xt plus sc equals 80. And then we've got xs plus sd equals 40. Okay, let's look at this first constraint. The first thing we can do is we know that we're going to increase xs, but xt is going to stay non-basic. Okay, and so we're going to cross out these xt's and we're going to put 0 there. And that's because xt is non-basic and it's going to stay non-basic. So we can essentially ignore that. Okay. Now, I want to essentially figure out what value of xs would make sf go to 0. Okay, and so if I want to find out when does sf go to 0, well, let's just actually set sf to 0. And if sf goes to 0, then I'll essentially hide that, and then I'd be left with 2xs equals 100. And so this is essentially saying, or if SF equals 0, then XS equals, if SS equals 0, then XS has to be equal to 50. Okay. Let's do the same thing here. Let's figure out if SC equals 0. So if I plug in 0 for SC, then XS equals 80. And then finally, if SD equals 0, then XS equals 40. Okay. So I've sort of figured out what value of XS would correspond to each of those slack variables going to 0. And the thing is, I'm sort of slowly raising XS from 0, and I need to stop as soon as one of these gets driven all the way down to 0, because if I go any more, that variable would then go negative. Okay. And remember, if we want to stay in our feasible region, all of our variables need to remain non-negative. So we can't go negative. We can go to 0, but we can't go past 0. Okay. And so looking at these, the first one that gets driven to 0 is this one. So this is the first variable that goes to 0. Okay, and so SD is going to be what we'll call our exiting variable. Okay, XS is entering, SD is going to exit then. It's the first one that gets driven to 0. Okay, and so we'll say SD is our exiting variable. And that SD leaves the basis. Okay, so that will tell us that then our new basis will be Z is still going to be there. And let's see, let's look at what our old basis was that we're going to essentially take SD's spot in that basis and put XS in that spot. I'm going to actually pretend like this basis has an ordering, because it sort of does. It has the ordering of our columns. And so our basis is going to be Z, S, F, S, C, and now XS. Okay, that's going to be our new basis. And now the trick is we need to do elementary row operations so that we get our standard basis vectors below each of these in our tableau or our augmented matrix. So I'm going to go ahead and set this up again. So Z, XS, XT, SF, SC, SD, right-hand side. Objective row, draw some lines in there. Okay. So what we want for this to happen is, let's see, we want XS to enter our basis. Okay. And so what we want to get is we want to get it so that, and it's entering in the place of XSD. SD had the fourth standard basis vector. So back here, maybe I'll flip it up like this, fold my page a little bit so that we can see this, where we were and where we are. Okay, this is going to help. Yep. So SD had the 0, 0, 0, 1 standard basis vector in it. And so that's the standard basis vector that we're going to eventually want in the XS column. Okay. And so XS, and let's actually label the rows. That'll help us maybe a little bit. SC, SF, those ones stay in there. And Z is always the objective row. Okay. So this is what we want here. Okay. Looking at what we have, if we look at the bottom row, it's got a 1 here. We want a 1 here. And so actually our bottom row in this case is good to go. If there wasn't a 1 here, we'd want to multiply or divide this row by whatever made this turn into a 1. Okay, and we'll see that an example of that in a bit. But this is a 1, and so we don't actually have to do anything to the bottom row. And so let's copy the bottom row up to here. And so this bottom row is then 0, 0. I'm trying to make this line up a little bit. 0, 0, 1, 40. Okay, so I just copied my bottom row down. Okay, now I look at this entry here, and it's a 1. I want it to be a 0. So if I want to zero this out, then I'm going to use a multiple of this row, add it up to zero that out. Okay, this value is 1, this value is 1. If I take this row minus this row, that should zero this out. Okay, and so I'm going to do this row minus this row. And so 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 1 is negative 1. And 80 minus 40 is 40. So I did sort of this row minus this row. Okay. Now looking up at the top row, or not, well, not the top row, the second row. I've got a 2 here. I want to turn that 2 into a 0. And so I'm going to take negative 2 times the bottom row, add it up to the top row. Okay. And so negative 2 times 0, add it up, and I'll still have 0 up here. Negative 2 times 0, add it up, and that leaves this as a 1. Negative 2 times 0, we'll leave this as a 1. Negative 2 times 0, we'll leave this as a 0. Negative 2 times 1, we'll change this into a negative 2. And negative 2 times 40 plus 100 will give us 20 here. Okay, so doing row operations, essentially maybe I'll kind of, here's maybe the way that I keep track of my row operations of, I took negative 1 times this row and added up there. I took negative 2 times that row and added it up there. And then I need to cancel this 3 out now to turn that into the 0 that I want there. And so I'm going to take 3 times the bottom row added up to the top row. Okay, so this is going to remain a 1. 3 times 1 plus -3, that's going to get me the 0 that I want. 3 times 0 will leave this as a -2. 3 times 0 will leave this as a 0. 3 times 0 plus 0 will leave this 0. 3 times 1 plus 0 will turn this into a 3. And 3 times 40 plus 0 is 120. Okay. So this is our augmented matrix or tableau after this process that we just did is called pivoting. So in pivoting, you essentially change one of your columns into a standard basis vector. In this case, we chose to change our XS column into the standard basis vector 0, 0, 0, 1. Okay, that brought XS into our basis. I'll maybe show you, yeah, that brought XS into our basis. Okay. So this is now our updated matrix. It's row equivalent to what we had before, so it has the same solutions and everything, but we've sort of changed where our nice kind of standard basis vectors are in here. Okay, so here's our new basis. I will say that our non-basic variables are xt and sd. SD because it left, and xt because it's still non-basic. Okay, and so those are both going to be 0 in our solution. And so reading off our new solution, each basis, each choice of basis corresponds to a corner point BFS, basic feasible solution. And so that new solution, we read it off. So essentially, the right-hand side encodes the values of Z, SF, SC, and XS. Okay, and that's because I'm essentially putting in zeros for XT and SD. And then if I put zeros in for those, then the only things that have a coefficient in this first row is the Z, in the second row is SF, and in the third row, SC, and then in the last row, XS. And so the new solution is Z, our objective value, has now increased to 120. Okay, that's going in the right direction. We went from 0 objective to now 120. SF, we can read off this value, is now 20. We've got 20 units of finishing slack. We've got 40 units of carpentry slack. And we are making now 40 soldiers. Okay, 40 soldiers and 0 trains, and we've got no slack for demand. We are making all the soldiers that demand tells us will sell. Okay, so this is essentially one step of the simplex algorithm. Okay, to kind of review what happened in this one step is we checked, is it optimal? We said no. We can improve it by bringing in XS or XT into our basis. We chose XS to enter our basis. We found which of the current basis variables gets driven to 0 first. And in this case, it was SD. So SD exited our basis. And then we had a new basis and we pivoted on that new basis. Okay, pivoted on XS to get to that tableau that represents that new basis. And with that, we got a new solution. Okay, now we repeat the process. So let's ask the same question again, which is it optimal? Okay, and so let's look at this top row. This top row says Z minus 2xt plus 3SD equals 120. Okay, I'm going to go ahead and move everything but Z to the other side. And so my formula for Z is I'll add 2xt to the other side and minus 3SD to the other side. plus 120. And so these two variables are currently 0. There are non-basic variables. And so if I look at them, if I were to increase SD from 0, it's got a negative coefficient, so it would decrease our objective. Not good, okay? We might have had a hint that this was going to happen because SD just left our basis and we improved when it left, so we wouldn't want to immediately bring it back in. It wouldn't provide any improvement right now. On the other hand, XT has a positive coefficient, okay? So bringing XT into our basis, increasing it from 0, should increase our objective, okay? So yeah, we want to choose. So is it optimal? Not optimal. XT can improve the objective. Okay. So here's actually the way I do it. And so we've sort of done it the long way. But what you want to do is scan this top row here. And for a maximization problem, you want to look for negative coefficients, okay, for these variables here. Looks like XT has a negative coefficient, which means that once we move it over the other side, it would be a positive coefficient and would increase our objective. Then what I do is I go ahead and circle that column, okay? XT is going to be our entering variable. And now we need to do this process again, okay? Here's the thing. To get these numbers over here, you'll notice that these numbers over here are exactly the right-hand side numbers divided by the coefficients of XS. Okay, and so that's all it is. And then we just chose the smallest positive one. So let's actually do that kind of as a shortcut here. So what we're going to do is we're going to take our right-hand side and we're going to divide it by whatever coefficient is in this XT column. And so we're going to do 20 over 1. We'll do 40 over 1, and we'll do 40 over 0. Yeah, if we've got a 0 or a negative value here, we ignore those rows, okay? It's not going to, that variable is not going to be driven to 0, okay? So we're going to ignore that one. And now we choose the smaller of the two, okay? So either SF or SC is going to leave. It turns out that by the time XT, yeah, as we raise XT, SF goes to 0 when XT is 20, and SC goes to 0 when XT is 40. And so we got to do the one that drives it to 0 first. And so SF is going to be our exiting variable. Okay, so I'll move this up here. XT is entering. SF is exiting, which gives us a new basis of, let's see, Z. XT is going to replace SF. SC is going to stay in, and XS is going to stay in. And then our non-basic variables are going to be, well, we just had SF leave and SD left in the previous iteration. Okay. Let's do another pivot. This time, so looking up at this, we sort of circled a row as our sort of exiting variable. We circled a column as our entering variable. This point here is going to be kind of what I'd say we pivot on this point, okay? Meaning that we want to turn this into a 1. Thankfully, it's already a 1. And we're going to want to turn everything else in this column into zeros. So that's the goal. I'll get myself a new sheet of paper here. and slide the, okay, actually, yeah. So let's go ahead and set this up and line it up right below here. So Z, XS, XT, SF, SC, SD, right-hand side. Normally, once I get the pattern down, I'll sort of line these up so I don't have to write my variables out again, and I'll just kind of have one tableau directly below the next tableau. And so if you have like a nice grid paper or something like that, that can be kind of nice here. Okay, so I'm going to want to turn this value into a 1. Turns out it's already a 1, and so I can leave this row alone. And so let me draw this line here. And then so this second row is going to stay as 0, 0, 1, 1, 0, -2, 20. Okay. Now, I like to think as little as possible when I'm doing these row operations because it's easy to kind of get messed up. And so I like to fill in right from the beginning as many entries as I can, just because I know what my next tableau is going to look like. Okay. And as long as you're sort of following the right rules, these values are going to kind of fill in the right way. One is I know that I want this column to become 0, 1, 0, 0. Okay, that's what I want it to become. I also know that my other basic variables, which let me write that basis along the side here, 0, x, t, s, c, and x, s. Those other basic variables are going to have the other standard basis vectors beneath them. And so my z column actually never changes throughout this whole process. The Z column never changes. If you wanted to sort of omit that Z column, you could, but it's just really there to remind us that we've introduced this Z variable. It will always stay 1, 0, 0, 0. Okay. This SC column is going to have the 0, 0, 1, 0. It's going to only have a 1 in the row that it corresponds to, the SC row. And then XS is going to have a 1 right here, but zeros everywhere else. Okay. And then from there, now I just see that I only have 1, 2, 3, 4, 5, 6, 7, 8, 9 things that I actually have to think about. Okay. So that's sort of a nice shortcut, is put my standard basis vectors exactly where they need to be. Okay. So this row already had a 1 there. It didn't need to be multiplied. It was able to stay the same. Okay, now I need to take multiples of this row, add it up and down in order to cancel out the different values. And so let's go up first. And so I've got a 1 here. I got a -2 here. So I'm going to take 2 times that row, add it up in order to cancel. So 2 times 1 added to the -2 will give me 0. That's what I want. That's why I chose 2. 2 times 1 plus the 0 is going to make this into a 2. 2 times -2 is -4, plus the 3 becomes -1. 2 times 20 is 40, plus the 120 is 160. Okay. Now I want to zero this value out here. And so I'm going to actually take this row times -1, add it down. And so take -1 times that row, add it down. So -1 times 1 plus 1 is 0. That gave me what I wanted. -1 times 1 plus 0 is -1. -1 times, that's going to give me my 1. -1 times 2 is +2, plus the -1 is +1, and -1 times 20 plus 40 is +20. Okay, looking at my last row, I want a 0 here. I've got a 0 there, so I actually can leave this last row alone. Nothing changes in this last row. 0, 1, 40. Okay, the last row didn't change. Okay. So there I go. I pivoted. This was a little bit quicker now this time. And as you get the practice, it'll move a little bit faster. You're just doing elementary row operations of taking multiples of a row and adding it or subtracting it to the other rows. And you're always going to essentially use your pivot row as I like to think of it as a tool. Okay. It's going to be what you're going to be adding and subtracting to your other rows to make things happen. Okay. New solution. We've got a new basis. Now let's go ahead and read off our new solution. Our objective value Z increased to 160. That's good. We should always see this, our objective value improving. XT, we can read it off this row. XT equals 20. SC equals 20, and XS equals 40. I'm reading those off the right-hand side because the other variables, SF and SD, are both 0. Okay, that's my new solution, my new basic feasible solution. It is feasible because I should verify all my entries are positive. Okay, all the variable values are positive, so I'm at a feasible point. Okay, am I optimal? Let's do what we did last time. So I said we want to scan the top row for negatives. Okay, so it was this sort of -2 that tipped us off that we should choose XT as our entering variable. Now, as I scan the top row, I see a -1 here. Okay, so we're not yet optimal. No. Essentially, that top row says that Z equals -2 SF plus SD plus 160. And so if I increase SD now, kind of one pivot into the future, it will actually improve it. And so although in our first iteration, we sort of moved SD out of the basis, now we're going to move it back into the basis. Okay. And as long as it's sort of one pivot later on down the road, that's sort of fine. And it's actually going to lead to an improvement. Okay. So we're going to have SD as our entering variable. We'll circle this column here. We can see that it's got a -1 in the top row, negative coefficient in the top row. It indicates improvement for a maximization problem. Now let's go ahead and compute our ratios. We take this number divided by the value in our pivot column. If we have a negative in our pivot column, ignore that one. We can't pivot on a negative, okay? So then we get 20 over 1 and 40 over 1. And so choose the smaller of the two. And so we're going to choose this one. Okay. So which variable is that? That's SC. So SC is going to be exiting. Okay. Now let's go ahead. I'm going to pause the video a little bit and rearrange my paper. Okay, I folded my paper over to kind of hide the stuff that we just wrote in the middle there so that I can have my two tableaus right next to each other. I also went ahead and kind of set up the edges, the labels on my tableaus. So this is our pivot column. This is our pivot row. We want a 1 here and zeros everywhere else in that column. So we want to turn this SD column into 0, 0, 1, 0. Okay. Turns out we got a 1 here. So we don't need to do anything to this row. If it were a 2, we'd divide by 2. If it were a half, we'd multiply by 2. Essentially, we'd multiply or divide this row by whatever we needed to in order to turn this into a 1. Got a little lucky. It's already a 1 again. And so we're going to have, we're going to leave it alone, and we're going to get 0, 0, 0, -1, 1, and 20. And now let's go ahead and fill in the columns that we know are going to be what they're going to be. So our basis columns are going to still be 1, 0, 0 for Z. My second basis column is going to be XT. My third basis column is this SD, and my last basis column is XS. And that's going to give me those. Okay, and you can verify that actually, because you'll notice that this row has zeros in all three of these places. Then as we add or subtract multiples of this row here, this SD row, it's actually not going to change any of the entries in these three columns because it's got zeros here. So that's why I can kind of quickly fill those values in. Okay. Now let's kind of go ahead and think about what we need to do to cancel out various values. Let's go up to the top row. We've got a 1 here, a -1 here. If I add this row up, that will cancel out the 1 here. And so I'm going to do 1 times this row added up to that row. And so that's going to be 1 times -1 plus the 2 is going to give +1. 1 times 1 plus 0 is going to be 1. 1 times 1 plus -1 is going to give me the 0 that's there. 1 times 20 plus 160 is going to make it 180. Okay. Next, we'll go ahead and zero out this entry here. I need to add 2 times this row up to that row in order to cancel it. And so I'll go remind myself that I'm going to take 2 times that, add it up to there. So 2 times -1 plus 1 is going to be -1. 2 times 1 plus 0 will be 2. 2 times 1 plus -2 is going to give us the 0 that we want. 2 times 20 plus 20 is going to give us 60. And that's good for that row. Now, if we think about what we need to do to cancel out this one here, we're going to take this row times -1 and add it down to here. Okay, and so -1 times -1 plus 0 is going to be +1. -1 times 1 plus 0 is going to be -1. -1 times 1 plus 1 is going to give us our 0 that we want. And -1 times 20 plus 40 is going to give us 20. Okay, so we finished pivoting there. We now have our standard basis vectors here, 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 and here. Okay, and now we can read off our new solution. So our new solution. Reading it off sort of for our first row corresponds is our 0 equals 180. Second row tells us that xt equals 60. Third row tells us that SD equals 20. Fourth row tells us that XS equals 20. And then because they're non-basic, we know that SF and SC are both 0. Okay, that's our new solution. Ask the same question again. Is it optimal? Okay, and we're going to scan this top row. There's no negatives. So the question to is it optimal? The answer is now yes. Okay, and that's because if we look at the top row and sort of move things over to the other side, Z is going to be -SF minus SC plus 180. And so if I were to increase either SF or SC from 0, both of those would have a negative effect on Z. Okay, Z, yeah, the best we can do for Z is actually 180. Increasing either of these would decrease our objective value. And so that is our optimal solution here, and sort of the end of the simplex algorithm. Okay, to wrap this up, I want to kind of pictorially show you what sort of happened in our feasible region. So I'm going to kind of sketch a quick sketch of our feasible region. Let's see. Okay. Not going to be perfectly accurate with this sketch here, but we started off, if we think of our variables as xs and xt, and we just sort of plotted in the original variables, we started off with both xs and xt at 0. And so we started at 0, 0 in the original coordinates. Then after one step, we moved to the point where we were at 40, 0. Okay, and then in another step, we moved up here to where we were at 40, 20. And then in the final step, we moved up to here where we are now at, no. Oh, 2060, yeah. So XS is 20, XT is 60, yep. So we went from 4020 to 2060 there. Yeah, and so what the simplex method does is it moves us around the boundary, sort of, if we had made the opposite choice in the first step, we actually could have gone from here to here to here and gotten there in 2 steps instead of 3 steps. But really, you don't know that from the beginning. And in practice, we're dealing with higher dimensional spaces, and it's more like kind of branching through kind of a bunch of edges on a hypergraph or something like that. But visually, you kind of want to think about is that we're moving from here to here to here each time, because our objective vector, or the kind of the direction of improvement, was sort of in was sort of in this direction here. We were always moving in a direction that offered us some improvement. Okay. So that will wrap up this video. The next video, we'll sort of talk about the simplex method from a bird's eye view and do some more practice.